Hello, this is Aliasing, here to let you know that I am continuing to work on this. Now, my first video where I went over the design and I was talking about the thing, lots of attention, lots of love, relatively, for an unknown guy. Second of me actually coding it, a little more niche, especially maybe because I'm new to Zig. I didn't really get to show off skills particularly much, maybe learning skills, but you know, today I just wanted to go over what I've been doing behind the scenes because I think it's a lot easier for me to write high quality code and to make good progress on this project when it's not live streamed. Now, what is it that I'm working on? Right. Well, here you can see the design. I've gone over this in a prior video, but this is the design. I can zoom in here for an 8-bit fixed width CPU, which to my knowledge does not exist. But why would I go through the effort of designing a CPU? Like, what's the point? Well, I want to create a fantasy console. I want to create a fantasy console based on assembly programming. I want to create the tools to program it. It's going to have graphics, it's going to have sound, and it should be a fun way to share projects around, share assembly coded projects around, and learn how computers kind of work the old fashioned way. I think of it as maybe a more fun version of NES development, right? So the goal is to create something kind of like Pico 8 but using actual assembly. Um, and I've made a video showing how I got this Zig project up and running. So that's great, but I think that having the time to really work on this and think about it and make it well has been a very good thing. Um, so for those of you who have watched the last video, um, I've done some things, right? So the way that this um, works, the way that this is going to work, and this will be very fun to design in my opinion, and there's a lot of different ways that we can slice it, right? But the way that this is going to work is that the CPU has its registers, the values it can kind of juggle around easily, but it operates on memory, right? So here's our memory. Ooh, that's a terrible shape. Look at how bad that is. Let's go. Here we go. Right. So imagine this is our memory, right? So we have 16 bits to work with. So here's our address 0. Here's our address of is it 16K? It's 65,536, right? So 65K, right? Or how about this? We'll be more assembly-esque. Call it OXFF, right? Now, you can make a lot of stuff, and NES developers made a lot of stuff using only a little bit of this RAM, right? Like, yeah, sure, this is 64 kilobytes of RAM, kind of, Yeah, sure, it's 64 kilobytes of RAM. That doesn't sound like a lot, but I think that we may have lost sight of the fact that when it comes down to it, the minimum entropy, the minimum information requirements for the majority of things that you do on a computer are far less actually than 64 kilobytes, which is how it used to be. And it makes it feel a little bit insane that we have gigabytes now. It makes me wonder what happened, but that's neither here nor there. This is the way things used to be. Love it or hate it. Obviously, couldn't do as much back then, but let's divide our memory up a little bit, right? And this is maybe not how we're going to do it in the end. I still have to do some planning and such, but let's say that here is, let's say that here's our RAM, right? This is RAM memory. So when we write to one of these addresses, right, from 0 to 0x7FFF, right? When you write to any of these, it will simply store it. And when you read from one of these, it will simply load it. No real side effects. It's just a store of memory, right? But now let's imagine for a moment that we have, and this is not how I'm going to do it, this is just explaining how things work. Now let's imagine that between 7FFF, so from address 8000, right? From 8000 all the way to A000 should be this address, right? This address range. So that's 2000 bytes, right? Range. Writing to this, maybe this is a screen buffer, right? Like maybe this is like a low resolution screen buffer right here. And yeah, I would make sure that you can write to the screen buffer, but I would also not necessarily make sure that you can read from it, but writing to it does something, right? And maybe this isn't just a screen buffer, like maybe this is divided up a little bit, right? So let's say that we're in, you know, this sort of region of memory, 0x80 something, right? And you write to 00, maybe that's like controlling scrolling in the X position, right? Or maybe, you know, 05, maybe this byte is controlling a color, right? Like maybe this is the red channel, you know, 06 is the green channel, and 07 is the blue channel for some kind of like palette register, right? And maybe 0x, you know, 80 is mapped not to a register that you can read, you know, like a write to, like a color or the scroll. Maybe this is something you read. Maybe this tells you, because we're operating on a scanning display, right? I'm going to use a scanning display model. I'm going to make a computer that, in theory, could run on like a standard 240p, you know, 15 kilohertz type monitor, right? And that's what all my like timings and such will be based on. Something where, like, in theory, you could make a box, maybe just an emulator box, like maybe just like a Raspberry Pi or something. But this box could be plugged in through like Composite or S-Video or Component, and it could be hooked up to a TV, right? So maybe address 80 gives us 1 byte. When we read from it, that will tell you which scan line you're on, right? Maybe it'll tell you your Y position. Maybe even there's like address 84 and 85, right? Just in theory, where writing 2 bytes to 84 sets up an address, right? So the first byte you write might set like 40, and then the second one 20, right? Pointing to like a source address. And then 85, maybe when you write a byte to it, it copies that many bytes from 4020 into like a buffer, right? So like maybe that like activates direct memory access, right? There's all sorts of different things that you can do with this magical mapped memory. And this is a common pattern in the 6502 that doesn't have like very sophisticated I/O, right? But in order for that to be reasonable, right? In order for that to work in a way that you would be able to pretty much like figure out what's going on, we need things to we need it to be clear when memory is being read or written, right? And that's done through our move instructions here, right? This is a very long way of explaining this part. Added cycle delays to the emulator and a quote-unquote pipeline, right? It's not a real pipeline. It's kind of like a 6502 type of pipeline, if you know what that is, right? But in order for the timings of the CPU to make sense, to correspond to what you might expect from a physical CPU, no guarantees, right? This emulator is probably realistic. I am not designing it with the knowledge that this design one-to-one could map to real hardware, but to the best of my ability, to the best of my understanding, it does, and it has the same characteristics as something that does, right? This emulator has to be accurate in one very particular way, which is when things are written to, right? Because imagine that you're writing to this color here, and this is a background color. Imagine this is a background color, right? So you're scrolling through your screen. Let's say your background color is currently set to red, and then all of a sudden you write halfway through the screen, you write 0 to the red color. Now all of a sudden it's drawing black, right? And so by changing this, like mid-picture, you've effectively created an image on screen where the top of the screen is red and the bottom of the screen is black, right? By writing to this. And that timing matters. That timing matters a lot. In the Atari 2600 programming, this timing matters a ton. In NES programming, this timing can really, really matter a lot. I'm going to make sure it matters, right? This is part of the challenge. So I will make it so that someone who doesn't want to learn cycle timings can make games and software reasonably well. But someone who does want to learn cycle timings will be able to get even more, squeeze even more juice out of this hardware, right? That's part of the fun and interesting challenge of this, right? So you imagine that the hardware has to take a certain number of cycles to do things, right? You can't do a bunch of things in one cycle unless those things are unrelated to each other and there's no sequential dependencies on each other. So the more you squeeze into one cycle, not only do you introduce complexity and the need for maybe like hidden values and things like this, and dedicated hardware to do specific things, but you also introduce redundancy in the hardware that hurts the simplicity of the design of the chip in ways that most chip designers would rather sacrifice an extra cycle here and there than to bloat the size of their chip, right? So this is a program that we had written earlier, which multiplies two numbers, right? So this is handwritten assembly, essentially, hand-assembled assembly to multiply two numbers. So what is this code? We load x and b. These are the two numbers we're going to multiply. We jump to the subroutine, multiply. This is something I've added since I was gone from the live streaming. We go to this subroutine, multiply the numbers in a loop. RTS, we return from the subroutine. The result of the multiply, you can see here, one operand in X, one operand in B, result in A, right? You could also say Y is overridden. Okay, so that's our call for this, right? You have to know how to call things. We call this by loading things into registers X and B. We get the result out into A. Then here I copy A into B. So A and B will both have the result of the multiply, which should be 42 because it's 7 times 6, and then we jump forever. I did not add a halt instruction. I will not add a halt instruction because we want this thing to break entertainingly, right? We want it to kind of keep going. We want like random instructions and random data to produce interesting results and make this machine a little unconventional in that type of way, where it adds entertainment value in that sense, right? So this is our binary. It's almost identical. There's like a few trivial changes in our emulator, right? And let's just show off what happens when we run it. So here's our execution. So let's zoom in on this execution. Shoot, do I have a broken scroll wheel? Yeah, I still have a broken scroll wheel, but here we go. So start out, we have a fetch delay, right? So it has to read the instruction from memory, right? It can't just execute it immediately out of RAM. That's not an option here. So it reads the instruction out of memory, right? And then it loads it. So it loads 20 from address 0, which is the start of our binary. You can see the start of our binary right here, right? And then it executes a bunch of instructions, and then it encounters JSR, which is jump to subroutine, right? This takes multiple cycles, right? So F1 is JSR, right? Our emulator has phases, right? It has phases. So fetch delay means what? It's actually all explained. It's all explained if we keep going down here, right? So fetch delay. The instruction cache is stale, so nothing can be executed, right? This occurs after a jump or a boot, right? In this case, a boot, right? But we actually get another fetch delay after our JSR because that's a type of jump, right? But what does jumping to a subroutine do, really? It has to do a lot. You have to push the current program counter, right? Push the current position of execution to the stack so that you can later pop it off of the stack to return to where the function was called from, right? Because you want to call a function and then go back to after where you called it from, right? So it has to use the stack for that, and then it has to jump to the address specified of the function that's being called, right? So a subroutine is a function. They're kind of the same thing. The main difference, in my opinion, between subroutine and function usually means that you have isolated variables, right? So you have like a different, like what they'd call like stack frame in modern programming. We don't get any of that, right? So that's why this is a subroutine. It's just a piece of code that you can go into, execute, go out of, right? But we have to use a stack because that's how it knows how to return from one thing and to another thing and to another thing and to another thing, right? But sorry for that. Good evening. Good morning. Now, fetch delay is one thing, right? Again, all these memory timings have to be accurate. That's the one thing that's accurate about this emulator. I don't really care if the content of a given register is accurate cycle to cycle, but I have to make sure that every memory access occurs on the cycle intended. So that's why my debug print has all these loads in it. That is pointing out that there is a load occurring on the previous cycle, right? So during this fetch delay, there's a load, right? And then on the next cycle, it executes it while loading the next thing, right? So the CPU can execute something and load something at the same time. That's not an issue for it if it keeps an instruction cache byte, which it does inside of next instruction, right? Normal execution, that's for any one cycle instruction. The majority of them are one cycle. And then we have our load store. We have an extra cycle for the index load store. If you followed along earlier, we have indexing for our load stores so that we can index into arrays of structs more easily, right? But that takes an extra cycle to calculate the address that we're referring to in our load store, right? When we branch, right, it takes an extra cycle because that's conditional, right? So the branch checks if this processor flag is set, and if it is set, it executes the branch. That's conditional, right? You can't just put that in a lookup table. So it takes an extra cycle to actually perform the branch, where it adds L, one of our registers, as a signed 8-bit number to our address in order to jump around like it does here. It jumps around our loop, to do a multiply, right? And it also jumps forwards when the multiply encounters a 0 rather than a 1, right? So here's our setup. We can see things are now loaded into registers. Content of B is 6, content of X is 7, right? And then it's going to start executing, jumps through the loops, jumping through the loop, jumping through the loop, jumping through the loop. And then, oh, look, now it's been shifting X over this whole time, right? I explained shift add multiply before, but you can look up the shift add multiply algorithm if you're curious what it's really doing. But now you can see that the carry is set to 1 and we don't get the same jump as earlier. Then we do execute our instruction 80, which adds B to A and writes it to A. A becomes 6, right? Still jumping around. And then we reach the end, right? And now A is 2A, B is 2A, and then we load up the address of our loop and we go through an infinite loop, right? We just jump forever to this FO right at the end of our loop, forever, right? FO does not stand for forever, but it's a funny kind of congruency here. And we just do that until we run out of the number of cycles I told it to execute, which is 200, right? So for those of you that are curious, I can put this source code up in a repo sometime soon. I plan on making this whole thing open source. But this is now our code for everything. I believe I've implemented the entire instruction set now in Zig, right? So we have our binary operations, unary operations. We can set processor flags for arithmetic. We can perform conditional branching. We can copy one register to another. We have CMP now, which lets us set processor flags based on whether things are greater than, equal to, or less than each other. So we can compare two registers. That's a very useful thing, right? And then one other wrinkle that results from having our accurate cycle timings is now all of our branches have to branch to one before where it intends to actually start executing, right? So, for example, if you look at this JSR mult, you can see it loads in 404D, 5050. So that's loading D into register L, 0 into register H, meaning it's setting us up with address D, right? Address 0D. 0D is 14, but our multiply routine right here is at address 15. This is just a side effect of how things are now because of this design, right? But now that we do have this design like this, we've opened up a whole world of interesting things, right? Say, for example, that now we want to, take our multiply loop and execute it in a constant amount of time, right? How would you modify your multiply loop so that it runs in a constant amount of time, so that you know what cycle that you're on at the end of it, right? And one way you could do it is to make it so that you can make sure, right, how many cycles this branch takes versus how many cycles this takes are the same, right? Are they the same, right? So when we're skipping over it, like right here, you can see, okay, we have how many cycles, right? We hit our can we get this bigger, please? Okay. Stay on top. So we hit our execute AF, that's down here. So here we go. Execute 90, 92, 40, 42, right? So AF is the point where they converge. AF is the point that it branches to. So 1, 2, 3, 4, 5, 6, 7, 8 cycles between 90 and AF when we do the branch, right? And then scroll down. Okay, here's us not doing the branch. 1, 2, 3, 4, 5, 6, 7. Aha! Right? So now we've observed, okay, when we do the branch, even though it's executing less code, right, performing the branch adds 3 cycles, whereas CLC and ADC only adds 2 cycles, right? So if we wanted our multiply to operate in a known amount of cycles, then we would have to put a no op here, right? Or put an operation that has no effect right here, but an operation that burns a single cycle, whatever that may be, right? As of right now, anything that isn't mapped in the instruction set is a no op, right? But now we know, okay, this loop takes 8 cycles to get from here to here, and we can do cycle counting, and we can have very exact precision with what we're doing. These are the type of considerations that I have to make in designing something like this. I cannot design this in a way that is just easy. I want it to be easy to get started. I want the skill ceiling to be extremely high, right, and require you to become very familiar with the instruction set. And I want to teach you a lot of the tricks that the old school programmers use to get more out of these. So in the future, I will be writing an assembler for this, probably for web, actually. I will probably be making this Zig code, this Zig emulator, run on web and have kind of a step-through debugger paired with the assembler on web, so you can program this architecture, which I'm tentative name FW8, just because it's a fixed width 8-bit instruction set. Not an amazing name, but tentative name FW8. You can emulate it, you can assemble it, you can debug it, all on one web application. That's the goal, right? So I will be writing an emulator in TypeScript, and if you watch this video and you want to see the process of me writing that emulator, um, not emulator, but sorry, rather assembler, right? This emulator will be running in WASM, Zig WASM. The assembler will be running in TypeScript, right? If you want to watch me write that live, then please let me know. I actually have already made some similar types of projects, so I'll probably base it on those. But once we get that up and going, we can get to some much more interesting things. For example, the GPU, right? And maybe the audio, right? Maybe we map some of this to audio, right? And maybe some of this audio is setting the waveform that we want to use, right? Or maybe some of it is setting the pitch of the waveform, right? And how do you do that, right? How do we want to make a flexible audio system that can make sound effects and music, right? That's simple enough that you could realistically have it on bespoke silicon at the time, right? Same with the GPU. How can we design this GPU to be realistic to the old hardware at the time? That's just something that I'm going to have to explain step by step to the best of my knowledge. And I'm hoping that some other nerds who know a little bit about this as well can come and help me ensure the accuracy of this project. I don't want people writing code for it and then finding out that I have some error that would make this completely impossible to run on old school hardware. Or completely impossible in theory, like on an FPGA or something like that, right? I don't want this to be an infinite execution space. I don't want this to be an irregular execution space where here you have like a bunch of very realistic things, and then here you have this weird extra feature that's sticking out funny, like in Katamari when you pick up a pencil and it's going all poop 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 poop, like where you you can implement like 98% of the CPU and GPU using like 7,000 transistors, but then this one tiny feature that you made that's really unrealistic, that's going to double it to 14,000 transistors just because you don't know what you're doing, right? Like that's obviously not that's not something that I would want to do, and that's something I'm going to avoid to the best of my ability doing. But anyway, guys, thank you so much for sticking to the end of this update. I know that it's just incremental. I'm just working on this progressively, but I just want you to know that this project is alive. I'm very interested in showing it to you. I'm very interested in teaching you about how these old computers worked. And until next time, this has been Aliasing. Thank you.